update. So we started with Lavoisier and his proof that air is not an element and earth and water are not elements. He didn't actually prove that much about fire, but he did try. I won't go into that. Air is not an element. I showed you last time that air is partly oxygen, partly nitrogen. It's important to know what the ratios are. Turns out that air is 80% nitrogen and 20% oxygen. Then Dalton, he revived Democritus's idea of atoms, and he was trying to explain the number pattern that he found in the way chemical compounds organize themselves. And he had the simple idea that atoms are like billiard balls, and that idea carried people very far. Mendeleev, he organized the elements into the periodic table, and the number of elements in each row followed this pattern, which you recognize as 2n squared. So the first row had 2, the next row had 8, 18, 32, and so on. Now, that of course raised many questions as what is the reason for the organization of the periodic table, and what is the reason for the number 2n squared, for the pattern 2n squared. And what this really amounts to, and which you will see in full glory today, is that it's the sign that the atom is not a billiard ball, that it has substructure. Okay, and we're going to be able to talk about how that substructure was discovered. And the main key to discovering the substructure of the atom was to realize that matter has electric charge. And so atoms have electric charge. And the signs of the electric charge were that electricity flows through water. We did the experiment about the breaking up of the water into hydrogen and oxygen by applying a voltage and flowing electric current through water. And we also had electric current flow through gas, and we'll repeat that today to look at the colors of the light that is emitted when electricity flows through a gas. And then near the end of our lecture last time, we talked about how Thompson measured the mass of the particles that move through the gas, or actually through the positive and the negative. Even when there's no gas, these particles move through as long as there's a vacuum. And those particles are called electrons. They're the basis of our electronic generation. Okay, when you say email, you're talking about Thompson, okay, electronic mail. So that's the basis of our technology today. And what Thompson did was he measured the atomic weight of electrons. And the way he did that was he deflected the rays of electrons with an electric field, and he brought them back with a magnetic field. I won't go into the details of that because that involves quite a bit of advanced physics. But basically, if he knew the forces that electricity and the forces that magnetism exert on the electrons, he could determine from that the mass of the electron. And he found that the mass of the electron was 1 divided by 2,000 times the mass of the atom of hydrogen. So that means that the hydrogen atom had a part to it. It could be broken apart, and the first part of it was electron. Now, what I did not cover was this, the work that came soon after Dalton by this gentleman, this Italian fellow by the name of Amedeo Avogadro. Okay? Not avocado, okay? But that's a nice way to remember his name, Avocado, especially since he talked about moles, and since you use avocados to make guacamole, you can remember that. That Avocado talked about moles, and we'll talk about what moles means. Well, since Avogadro, he started as a lawyer. I fell into my own trap. Right. Avogadro started as a lawyer, and later on he abandoned that. And became interested in mathematics and physics. Later on, we'll see there was another physicist, astronomer, who followed the same path. His name was Hubble, by the way. I'm sure you've heard of Hubble. And in 1820, he became the first professor of physics in Italy. So Italians really revere Avogadro. Okay? Now, what did he do? Well, first of all, he applied a little bit of lawyer-like logic to what Dalton had already thought about and Lavoisier had already thought about. And that was that, you have oxygen in the air, and sometimes you have hydrogen in the air when you put metals into acids and so on. And he thought that since oxygen and hydrogen so readily combine with each other, that they are kind of very active elements, and so why doesn't the oxygen in the air not combine with itself? Okay? And he came to the conclusion that oxygen cannot really be free in the air. It's not monatomic. It actually exists in the air as a molecule. He coined the word molecule of oxygen, in that two atoms of oxygen pair up, so that now the entity of the molecule of oxygen is not as reactive. Okay, so it doesn't pair up and go make O3. Actually, you can make O3 in the lab. Does anybody know what O3 is called? You do need it in this atmosphere. It's called ozone. Okay, so ozone layer is the O3 layer. It's up there. But it's broken up by ultraviolet light, so we don't have it down here. So O does tend to combine with itself. And similarly, H doesn't like to stay alone because of its ability to combine with other atoms. And so it combines with itself too. And so naturally, H exists more like H2. Okay, so these are the molecules of oxygen and hydrogen. So that was his first hypothesis, which is a very, very good hypothesis. It turns out that it's absolutely true. But now I'm going to tell you about his wonderful discovery. And his discovery was based on the idea that if you have a molecule of hydrogen, then if you have this table of atomic weights where you're comparing how heavy the atoms of the different elements are relative to the atom of hydrogen. So the atom of helium is 4 times heavier than the atom of hydrogen, which means that since the molecule of hydrogen is H2, that means that the molecule of hydrogen has an atomic weight of 2, because there are 2 of these guys. Okay, so it's 2 times heavier than hydrogen. And similarly, the molecular weight of oxygen, O2, is not 16 down here. It's not 16, but it's 2 times 16, because they're 2 combined together, so it's 32. We don't have his discovery yet. That's just common sense, right, from the table. Okay. Now, another output of common sense is that suppose, now this number 2 doesn't mean anything. It just says that this molecule is twice as heavy as hydrogen, which is the lightest. That's all it means, okay, 2. However, if I say that let me collect 2 grams of oxygen, okay, so I put them all in a balloon, and I weigh the balloon until the balloon weighs 2 grams, not in air, but I take it away and weigh it carefully somehow. And I actually collect 2 grams of hydrogen, oxygen rather, hydrogen. And then I also collect, so I collect 1 molecular weight of any gas, like hydrogen or oxygen. Then, since that's 1 molecular weight in grams of hydrogen, or 1 molecular weight in grams of oxygen, these 2 containers that contain 1 molecular weight of each of these gases must contain the same number of molecules. Is that common sense? Right? Because you got twice the weight of this guy, and each atom weighs twice as much as, each atom weighs 32, each atom weighs 2. So the number of molecules here is the same as the number of molecules here, because I took this to be 2 grams hydrogen, and I took this to be 32 grams of oxygen. Now here's the great discovery. Okay? The great discovery is that 2 grams of hydrogen occupy a fixed volume, 22.4 liters. And 32 grams of oxygen, which is the same number of molecules, also occupy 22.4 liters. So the volume occupied by the same molecular weight of any gas is always the same, as long as the temperature and the pressure of that gas is the same. And the thinking there is that each molecule of gas is kind of behaving the same, independent of whether it's hydrogen or whether it's oxygen or whether it's nitrogen, because it's behaving like a billiard ball flying around. Okay? So this billiard ball flying around is the same as another billiard ball flying around. It doesn't matter that it's oxygen or that it's nitrogen. There's still billiard balls flying around. Okay? Just a little bit of billiard compound flying around. So therefore, if the number of molecules is the same in 2 grams of hydrogen as the number of molecules in 32 grams of oxygen, we should expect them to occupy the same volume as long as they're flying around at the same speed, which is your temperature, or the same pressure. So that was his great discovery. And that was a very important discovery. And so then he generalized that the volume occupied by one molecular weight in grams of any gas will always be the same, 22.4 liters, okay, at standard temperature and pressure. Why? Because of common sense, all right? Because 22.4 liters of the gas contain the same number of molecules rattling around with the same speed. Okay, that's the basic idea. All right. Now, how many molecules do you have? Right? We still have this question: how many molecules? And that Avogadro did not find. We will do this later, but we will get the number today. And that, by the way, in honor of the great Italian who thought about it, it's called Avogadro's number. Okay? So the number of molecules in one molecular weight of any gas is Avogadro's number. And the volume is 22.4 liters. But we'll derive that later. But before we do that, oh dear, I got rabbits. This is the problem of translating from PCs to Macintosh. Okay, please, A, B, C, D, okay? A, B, C, D, E. All right, just be logical. All right. So there's your first question. Think carefully. I've already given you a piece of information. Use that. What is the average molecular weight of air? What would 14 be? 14 would be this guy, which would be nitrogen, which would be the atomic weight of nitrogen. But air is not N, right? Air is N2 plus O2, right? So it can't be 14. Can it be 28? Well, it would be 28 if it was N2. But you know it's not only N2, there's some O2. So it's not 28. Can it be 16? Well, that would be O. It's not O. Could it be 32? Well, that would be O2. It's not O2 because it's N2. So you need O2 and you need N2. So how much N2 and how much O2? Well, I told you, and I told you, remember this, 80% O2 and 20%, sorry, the other way around, 80% N2 and 20% O2. So it's mostly N2, which is 28, and the little bit of O2, which is 32, jacks it up to 28.9, which is 29 is your best answer. So how did you guys do? D, D, which one is the A, B, C, D? 32. Okay, all right, all right. So anyway, so now I will continue the search from last time, and I will now talk about 3 or 4 wonderful new discoveries that have completely dominated our civilization. Okay, one of them was, of course, electrons. The next discovery I'm going to talk about is X-rays. In this tube that Thompson was working with, you have this ray of electrons, right? Now, when this ray of electrons hits this phosphor screen at the end, the ray of electrons comes to a stop, okay? And when it comes to a stop, some of the energy of that electrons is converted to some other rays. And that was what was discovered by this guy, Röntgen, okay, German physicist. And he discovered it by accident when one day he had his hand there and he was running the Thompson tube, and he put his hand on the photographic plate, and later on he developed the photographic plate, and by golly, he could see his bones, right? And his wife's wedding ring on this. It was a nice secret discovery that he made. He worked on it for a month or so, and then he showed his wife, and his wife was really excited, and then he announced it, and the whole world was excited that you can actually see through the human body, yeah? Like the comics of Superman. But this guy came first. And of course, when you go to the dentist, you see through your teeth for cavities and so on. X-rays are a marvelous tool for our civilization. Now, what physicists have used the X-rays for is not only to look at the not only to look at the human body, the skeleton and so on, but also to look at the inside of atoms, okay? Or inside of virus molecules, and to determine, to unravel their structure. Okay? So in other words, when we want to cure diseases, we need to know, where are all the atoms in this molecule so we can construct some drugs to deal with these diseases. But just to make life simple in the beginning, if you take a crystal of something, for example, if you take a crystal of salt, it's a cube, and when you penetrate with X-rays, you get a nice pattern of deflected rays. Because when the X-rays hit the individual atoms, the X-rays deflect in a particular pattern called the Bragg diffraction pattern. And when you collect this nice pattern, from there you can deduce what is the atomic structure of sodium chloride, which is salt. Sodium chloride, Na and Cl together. That's the atomic structure of sodium chloride, which is... this is very important. This was not done... I can now use this information to determine Avogadro's number. Okay? Because now I know how big the volume is of 1 mole or 1 atomic weight of something, or like sodium chloride. So here's the answer. Avogadro's number is this huge number, say 6 times 10 to the 23. So, will you please take a deep breath? Okay, let it out. Do you feel any more spiritual? Do you feel any more scientific?
Not really.
Well, turns out that you just breathed the same molecules of air that Jesus breathed when he was alive. Some of them. And it turns out that you also breathed the same molecules of air that Einstein literally breathed when he was alive. So you should have felt both spiritual and more intellectual after that deep breath of air. Now, the reason you are breathing what Jesus breathed and what Einstein breathed is because the number of molecules is a lot. Okay? So what I want you to do for your homework problem at the end, number 3 and number 4, is figure out how many molecules of Jesus' breath or Einstein's breath. I put the problem as Einstein's breath. How many molecules of Einstein's breath did you actually take in? Right? That's your problem. But I won't divulge how to do it. It'll take some thinking, some work. Okay. All right. So, sorry. Let me come back to that. So I need to show you how they got Avogadro's number. There are 2 ways. I won't show you the hard way. I'll show you the easy way. And this easy way came later, because X-rays came later. Okay. So the easy way is to do an X-ray of the sodium chloride molecule and figure out how many sodiums, the yellow, the blue ones, and how many chlorines. Maybe it's the other way around. How many chlorines there are? Yeah, I think it's chlorine and sodium. How many there are in each cube of the cell, the unit cell, they call it, of sodium chloride. So then what you do is you say that first of all, the atomic weight of 1 unit of sodium chloride is 23 plus 35, because the atomic weight of sodium is 23 and the atomic weight of chlorine is 35. So the atomic weight of sodium chloride is 58 if you had 1 molecule of sodium chloride. 1 sodium, 1 chloride. Okay? I've got several in this cell, so I'll have to take that into account. All right. Also, you can grab some table salt and use Archimedes' method and measure its density. So we can measure the density of salt is 2.2 grams per cubic centimeter, which means it's 2.2 times more dense than water. So there's the density. Now, if the salt was a gas, then it would occupy 22.4 liters of volume. But it's not a gas, it's a solid. So that's why it occupies a smaller volume. So if I take 1 mole, 58 grams, of sodium chloride and use the density, then from the weight, 1 mole would mean 58 grams. Okay? 1 molecular weight in grams. I take 58 grams of salt, then I can figure out the volume of 58 grams of salt because I know the density. The volume will be about 30 cubic centimeters, not 22.4 liters, okay? Because it's not a gas. All right. Now, X-rays show us the structure. And they show us in further that the side of this cube, the first smallest cube, is 5.64 times 10 to the minus 8 centimeters with 4 atoms of sodium and 4 atoms of chlorine in there. Okay? So 4 atoms of sodium chloride in 1 unit cell. So then I can figure out the volume of 1 salt crystal from this X-ray picture, that the volume would be the cube of this number because it's a cube. Okay? 1 side cube. So the volume is 5.64 times 10 to the minus 8 centimeters cube, which is this number. 5 cube is 5.6 cube is 179, and 10 to the minus 8 cube is 10 to the minus 24. So in section, they will help you work with big numbers. And we will work with big numbers to find out how much of Jesus' air you breathed. Okay? So you'll need to know that. So once you know the volume of this cubic cell, you know the volume of 58 grams, you can divide the two, and you can tell how many cells you've got. Okay? So if you divide these two numbers, it says you've got 1.6 times 10 to the 23 of these cells, single cells, all across your 58 grams. But now remember, these are 4 molecules of sodium chloride. So I multiply by 4 to give us a total of 6.5 times 10 to the 23 molecules and that's Avogadro's number approximately. So you have fun with that and the problem that I gave you. That's why I want you guys to work as a team, because some person might think I need this, some person might think I need that, and you can pool your brains together. Now, so after Rankine discovered X-rays and lots of wonderful applications, of which I just showed you one, people became interested in the question of, do you really have to have this tube to make X-rays? Do X-rays occur naturally? And there was a lot of interest in salts that fluoresce naturally. So there was well-known salts of uranium, which you've left them out in the sun and you brought them back in the room in the dark, then they would glow. In fact, in the old days, when they made your wristwatches, they would paint these numbers a little bit with a little bit of uranium or something, so that it would shine in the dark. Yeah. But anyway, so people try to find out, is there some substance which may automatically naturally emit X-rays? And it turns out that there were lots of substances that emit X-rays. And this was the discovery of what we call radioactivity. And the most famous person for radioactivity, of course, is Madame Curie, because she discovered major radioactive elements. Okay. And this is Madame Curie in her laboratory working with her husband Pierre, and she in fact took tons of this stuff, okay, tons of this stuff to purify, to make a tiny bit of to take a tons of this stuff to make a tiny bit of radium or polonium. Okay. So Madame Curie worked in the laboratory to purify and isolate 2 elements, 2 new elements. Both of them were radioactive, radium and polonium. And these emit X-rays, okay? And also, they emit other forms of radiation, which I'll talk about. For example, they emit electrons, like the kind that were in the Thompson tube. And they also emit other radiation. And she didn't know too much about that. And eventually, that radiation hit her skin and her heart and her lung and so on. And she eventually got cancer and she died. So if you work with radioactive substances, be careful that you don't, that you're well protected. Okay, if you go get a job in a radioactive plant or something like that. All right. So here I have some radioactive substances in this lead container, and I'm going to use this counter here. I don't know if you can see it. I may have to take the lights off actually to do this, but I just wanted you to see this counter. And you can see the lights on this counter when you start seeing can you see the lights now on this counter? All right, you see there's a 4, 8, 1, 0, okay? And they kind of, let me actually reset them so they start with 0, okay? So they're all 0 now. And now what I'm going to do is I'm going to open this thing and irradiate all of you. No, it's very weak, okay? It's very weak. And in fact, most of you who have a smoke alarm in your house, you probably have a radioactive element in the smoke alarm, okay? So I'm not doing any harm. So I'm going to take some of this radioactive material and bring, in fact, I'll just take this counter and bring it close to this guy. Okay, and you can see that this counter now counts a lot of these stuff, all the stuff coming out of here. Okay, if I take it far away, you see it's gone. So this stuff in this container is all radioactive. I will not invite you to come and play with it. Turns out that the amount of radioactivity I'm getting now, because of the opening of this lead container, is less than what I would get if I were to take one trip from here to Chicago in an airplane. Because there's a lot of natural radioactivity in the universe that's coming down to the Earth. And that's what you're looking at there, is the natural radioactivity in this universe. But now I'm down at sea level, so you're not seeing much. But if I go up in an airplane, it'll go up a lot more, and I'll get radiated. And if I take a lot of trips, I'll eventually get as much radiation as I just took. So it's not serious. But we'll come back to this radioactivity some more. as we proceed. Now, this is your second question. So we stop it. And I think it's pretty obvious, right? What's the answer? Good, good. Okay, D. When the atoms of radium break up, the fast particles come out, and I'll show you that. And those are what were used to determine this more about the structure of the atom. Okay, we're all talking about the structure of the atom. Okay, so the person that used these munitions that came out of radium was Ernst Rutherford. Okay, so what Rutherford did, first of all, was he was working with radium, and he was trying to understand the kind of radiation that came out of it. And he identified, by using electric charge and plates and so on, that there were three types of rays that came out of radium. That there's three types of rays that are coming out of here. Okay, one is the good old electrons that Thompson discovered, and that had negative charge. Okay, that's why he called them, I don't know why he called them beta rays, but he called them alpha, beta, gamma, and beta turned out to be the negative electrons, okay, that Thompson had found. One has zero charge, so it was not deflected by a plate of charge. And this was the same as X-rays, which we also call gamma rays because it's more powerful. And the other one was brand new discovery. He found positively charged particles of stuff coming out of the radium. And this positively charged particle that he called, this, as I said, he called electrons. This was, of course, the X-rays. And these positively charged particles he identified later on to be actually the nucleus of the helium atom. So if you've got uranium or you've got radium, right, it turns out that the reason that it's radioactive is that it's got so much stuff in it that it breaks itself apart, and then you have a daughter nucleus and a particle of 2 protons and 2 neutrons, which we'll talk about, that come out. And these are actually the nucleus of the helium atom. And he used these to understand the structure of the atom. So how did he do that? So what he did was he said, if I want to know what is the structure of the atom, I'm going to take something really thin, maybe one layer of atom, and I'm going to blast it with these particles that are coming out of my radium. And then I should be able to find, remember how the question was, if matter is charged, and you have all these electrons inside and these atoms, where are the electrons? Okay, are they kind of all over? Are they distributed? Where is the mass of the atom? What is the structure of the atom? You're sort of taking, like, if you want to know what is the structure of this watch, you could sort of unscrew it and take it apart gear by gear. But he didn't have those tools to unscrew the atom, and take it apart. So what he did was he took a hammer and he banged it, and then the stuff that flew out, it gave him a hint of what was inside the atom from the stuff that flew out. So these alpha particles are like hammers, okay? And what he was expecting to happen, this is Rutherford and this is his colleague Marsden, I think, that was doing this experiment. What he was expecting to happen is that these alpha particles would go mostly straight through. And a lot of his students were doing experiments. Marsden was one of his students. And so here was his radioactive source, and here was a detector that would pick up the alpha particles by measuring their charge. And he expected most of these alpha particles to come over here, and from these deflected zones he would be able to tell what's going on inside this gold foil, which, by the way, was very thin, so it almost consisted of just like one layer of atoms. Now the big surprise was, and see if I can show you this movie. So I better put it in projection mode. So you can see that when the alpha particle goes through and hits the opposite side, it lights up this phosphor-coated material, but occasionally the alpha particles get deflected. Yeah? And so he had students studying this stuff as to how many alpha particles go in which direction. Are you noticing anything unusual about this picture, about this film? Okay. So then this new graduate student joined him, and his name was Marsden. And Rutherford was a pretty egotistic fellow, and he didn't really believe that this graduate student was worth anything. So what he did was he told Marsden, you know, everybody's doing important experiments and I don't want to bother with you too much. So why don't you go and find out, you know, everybody's measuring over here everybody's measuring over here all these, how many particles are coming out at what angle. Why don't you just put your counter over here and see how many particles are coming, you know. Now keep yourself busy, you know, just like the teacher who told Gauss, you know, add up the number from 1 to 100 and come back when you get the answer. Well, Marsden came back and he said, you know, I found a few particles going backwards. And Rutherford said, baloney, that can never happen. You know, these particles are going through the atom. They're very energetic. You know, you're lying. Go measure again. So Rutherford went back. And Marsden went back and he started to measure. And, you know, you have to be in a dark room and no lights and so on. And Marsden was in there looking very, very hard. There are only few of these that go this way, okay? He was looking very hard. And what Rutherford did was he went into the room quietly and he removed the source. He wanted to test Marsden to see if he still comes back and says, I see stuff, yeah? So Marsden came back and says, you know, you were right. I don't see anything. So then he said, oh, go look again, go look again. So he went back, he put the source back. Marsden came back and says, yeah, I see a few sometimes, you know. Like for every 10,000 of these hits, Marsden would catch one. Right? See how careful he was. One part in 10,000 goes backwards. Right? And so now he said, Rutherford told Marsden, okay, very good, go have lunch. And then he tried to figure out what was going on. And what Rutherford figured out, and this was his great discovery, is that the structure of the atom is such that its entire mass, it looks like this big a billiard ball, but the entire mass of the billiard ball is inside one small region called the nucleus. And the reason that most of the particles go straight through is because most of the time they miss the nucleus. But if 1 in 10,000 particles happen to hit this small, tiny, tiny little nuclear area, they'll bounce back. And so from Marsden's experiments, he figured out that the structure of the nucleus is that the structure of the atom is that there's a very small part. This part is the region for the electrons, and this part is the region of what he called the nucleus. And so he says, okay, all of this blue stuff over here, which is the mass of the atom, is all concentrated in the nucleus. And these electrons are somewhere dancing around somewhere in free space, okay, which make up the atom. He didn't know what the electrons do, okay, but he knew that all the charge, all the positive charge, and all the mass of the atom, of the billiard ball, is really here, and the electrons. So it's the first time that he got an idea what the structure of the atom looks like. Now, exactly how the electrons are distributed is a whole new story, okay, which we will come to. But this part of the story, that the nucleus is the mass of the atom, I want you to try and appreciate a little bit by looking at this picture. So here's the stadium, right? So if this stadium were the hydrogen atom, okay, if this stadium were the hydrogen atom, the entire hydrogen atom, right, then the nucleus would be a tiny little pea. I'm sorry, this is a baseball stadium. A tiny little pea on the pitcher's mound, okay? So the entire atom was the stadium and the parking lot, right? The nucleus would be this tiny, and all the mass is in there, okay? All the mass of the nucleus of the atom is in the all the mass of the atom is in the nucleus. Most of the atom is empty space, okay? It contains 95.95% of the atom's mass over here. Okay, and what are the electrons? The electrons are sort of like ants crawling around this picture. Okay, the really tiny things crawling around this picture. That's the picture of the atom, right? So now, we really have to focus now on the electrons. Where are the electrons? What are they doing? Okay, and this is where we come to, again, several major, exciting new discoveries about physics. Okay, already the nucleus is very exciting, right? Because it generates nuclear energy, and you can use it for destruction of things and so on. I won't go into all those nasty stories. But now the big question is, we went from elements to atoms to nucleus, so now we're going to talk about electrons. Where are the electrons? Yeah, what are they doing? And then later on, after that, we'll talk more about the nucleus, namely the nucleus consists of protons and neutrons, and then later on we'll talk more about the fact that protons and neutrons consist of quarks also. So these would be nice examples for you to think about as possibly discovery examples. If you're looking for material to write your paper on, you don't have to use this, okay? But it's just an example of how these discoveries were made that will be useful for you. So we're coming now to different areas of physics, okay? Several disjoint areas of physics come together to shed light, literally, on what the electron distribution is like in the atom. So last time I showed you when you have a gas and you pass electricity. Here I have some xenon, okay? I've got some xenon, and I put it in this high voltage and I turn it on, and you see that it's got a light comes out, and the light has a certain color, okay? The light has a certain color. Now if I change the gas, right? If I change the gas, then I have to remember to turn the voltage out before I play with it, otherwise there won't be any more lecture. All right, now I will take this one. I think it's krypton. Okay, it's krypton. So now we're going to take a different element called krypton, and it has a different color. And now we'll take another different element. Let me put this back so they don't get all my elements don't get mixed up like in the periodic table. And now you get this brilliant red light, okay? So you can excite atoms by using electricity like I'm just doing, or you can excite these atoms by throwing them in a flame, and they give out wonderful light of different colors. Okay? And so this then tells us something about what's going on inside the atom. So from the light to figure out about the electrons is a huge step. Okay? And so I'm going to go through it rather slowly. Okay? So when you get these colored images, what is going on? Different elements producing different colors. So what's going on? First of all, we need to know what is color. Okay? So now you know a little bit about color from your experiments and reading in high school, or we've shown you pictures of the rainbow. That's why I had the picture of the rainbow in the beginning of this part of the talk, of the lecture. So if you take, this is a discovery that Isaac Newton made. Okay? By the way, Isaac Newton made this discovery at the age of 18 or something, right? So he was going to a university like Cornell or Cambridge at the time. And Cambridge was inflicted with the plague. And at that time they didn't have, a cure for the plague. So they just closed the university down and said, everybody go home so you don't start passing the plague around. And so Newton was very excited about learning new things. And so he went home to his country garden in his home in Lincolnshire. And in the garden, he saw the apple fall, and he came up with the idea of gravity. This is all at the age of 18 to 20, okay? And inside his dark room, he tried to figure out what is light. Okay? And he did this experiment where he took white light, because people thought that this white light that the sun gives us is pure light. And he took this white light and he put it through this prism, and he saw the different colors of the rainbow. And then he realized that this light is really a mixture of all of these lights. And what the glass is doing is the glass is bending the light. Okay? And it's like when you put a pen or a pencil in a beaker of water, it looks bent. Right? So the glass bends, or the water bends the light. So this prism, this glass prism, bends the light, but it turns out that it bends each color a different amount. And that's called dispersion. Right? So if it bends the blue the most, so that's why the blue separates from the red bends the least. And so that's why the white light is broken up into its spectrum. Okay? So this people knew, of course, from Newton's wonderful work, that white light is a mixture of the colors of the spectrum. But what really is light, understanding that came much later, but I'm going to jump the gun and tell you what people understood light to be. They understood light is actually a wave. A wave of what? Like if you have water, you know that when you throw the stone in the water bounces up and down, right, to make these nice ripples. So here you have water waves. And you can say, when you have a water wave, that you have wavelength. Wavelength would be the distance between two valleys or two crests. And that would be the wavelength. Well, what light is light is essentially a wave. But the wave is not waving in water. A wave is waving in vacuum. So, but a vacuum is nothing, right? So what's waving? So we'll do that when we come to chapter 4. What's waving is electricity and magnetism. Okay? So electric and magnetic waves are waving, and the waviness of electricity and magnetism give you light. And to give you that scale, I want to show you that you have many kinds of electricity and magnetism waves. In fact, you probably use some every day when you heat up your water or you heat up your food, your leftovers, your pizza, etc. You use microwaves, right? So microwaves are electricity and magnetism. When you call your friend on the cell phone, you use probably radio waves or megahertz. What the hell is megahertz? Anyway, see here somewhere. And light is in this range here of wavelength. Okay, this entire spectrum of visible light is scrunched into this region where the length of the waves, or the wavelength, is in nanometers. Okay, so not meters, but nanometers. So if I go back to the previous picture, red light will be 600 nanometers. The distance between here is 600 nanometers. And blue light will be 400 nanometers. But just to give you a feeling about where light is on the entire what we call electromagnetic spectrum, light is this tiny region over here. Then beyond that, you have ultraviolet light, infrared light is on this side, and then you have gamma rays and so on. So we'll talk about all this more later. I just want to show you that light is a wave. Now, how do I know that light is a wave? There are a couple of important properties about waves. One of them is called diffraction. So if you have a wave, and the wave runs into an obstruction, the wave can go around the obstruction. So for example, if I take off my microphone, okay, I'm going to do that now over here. I won't take off the VideoNet microphone, okay? So if I take off my microphone, you can still hear me, right? But what if I now go behind an obstruction? Hello, can you hear me? You all laughed. So that means you could hear me, right? So the waves hit the obstruction of the desk, but they went around it, right? So when you go to a symphony and they give you a bad seat over here, right, instead of having one of the good seats, you know, it turns out you're going to listen to Zubin Mehta or something. So you take the seat, the free seat, and then you can still listen because the sound waves bend around obstacles, as long as the obstacles are not huge compared to the wavelength of sound. Okay, and the wavelength of sound is rather large, and so it can bend around. So that is called diffraction. Now there's another property of sound waves. We'll show you that light has these properties also, okay? But first I want to show you another property of sound waves. And I'm going to show you this second property of sound waves by doing an experiment, okay? And then I'll give you the name of this property. And the experiment is that I'm going to make you listen to two different sounds, okay? That's one sound. And here's another sound. Same, right? Not exactly, okay? Now listen together. I'm going to turn them on together. And listen carefully and describe what you hear. And now comes the question. If you get a headache, let me know. All right, so hopefully you guys all said that you hear it loud and soft, loud and soft, loud and soft, loud and soft, right? Okay, that's what you're supposed to hear. Alternates between loud and soft. It's called beating, okay? Not the beating of your heart, but the beating of the sound waves from each other. That's E. How do I put this away? Hide, okay. So now, what I'm going to do is I'm going to show you that these two properties of waves, which are manifested by sound waves, are also manifested by light, and therefore light is a wave. Okay? So first property is diffraction. Then I'll just show you a picture. You take a razor blade, right, and if you run the light into an obstacle that's very large compared to the wavelength of light, then the obstacle will block the light. There's no light on the other side. However, if you run the light into an obstacle which which is comparable in length to the wavelength. So for example, the corner of this razor blade, then you can see that at this corner, the light is gotten through. Right, so it's not completely sharp corner. Here this is bright, and here this is dark. This is bright, this is dark, this is bright, this is dark. Just like that's actually the same thing going on over there. But the point is that it got around the corner to illuminate the backside. It illuminates the backside of this razor blade. Same thing over here at all these other sharp corners. So this is a result of diffraction of light.
Now this slide contains the apertures I'll be using, and in fact the first one is just 60 micrometers wide, or 60 microns for short. That's about 1/16 of a millimeter. So if I place this slide in front of the laser beam, you'll see the diffraction pattern on the screen over there. The aperture is aligned vertically, and that sharp spot of light has clearly been spread out or diffracted in a horizontal direction by the small aperture.
Now I'm going to show you the interference of light. I'm going to use this, let me put it in projection mode, and I'm going to use this laser and shine it on this disk, okay? And can you see the light and the dark? Let me try to rotate this pattern. Can you see the light and the dark spots? The light, dark, light, dark, light, dark. Okay. If it was light, and what this disk is it's a CD or a DVD. You can do that yourself with your homemade laser and impress your friends. It's just a CD or a DVD. And what I did was I shone the light on this DVD, and the DVD has grooves on it, burnt by the laser. Yeah. So these grooves act like sources of light, which are really close together. And if you have two different sources of light, just like those two different sources of sound, but really close together, they interfered with each other to give you loud, soft, loud, soft. So you have light, dark, light, dark, light, dark, which is the interference property of light. Okay, so light as a wave demonstrates interference and diffraction. Okay, another experiment you can do at your leisure is make a very small slit with your fingers by putting the fingers together, and then hold that slit up against a bright light, for example, the white over there, and you'll see the dark, you'll see this kind of dark light pattern due to the interference of light. So what's happening is that light is coming from two different sources nearby, for example, like the two sound waves, and then when the light waves arrive, when two crests come together, you get a high crest, and when a crest and a trough come together, you get nothing, darkness, and you get medium light, and then when two troughs come together, then you get darkness, and that was the laser demo that I just did. So just to convince you that light is a wave. Now come back to this whole problem, the whole business about the color of the elements. So this was Newton's experiment with white light. If you did Newton's experiment with the light coming from the element, not the white light from the sun, if you did that same experiment, then you would see not the spectrum, but you would see a series of lines, right? And to see for yourself this light and look at these lines of different colors, these what we call spectral lines. So when an element is introduced into a gas discharge, it gives out light of different colors, but not like the spectrum, but a discrete set of lines. Okay? And if you really examine that very carefully, you find that sodium will look like 2 yellow lines, and calcium will look like purple lines, then red lines, and so on. Lithium, strontium. Every single element that you can fire up in this gas discharge tube has a different spectrum of light, which is called the line spectrum. And this brings up this huge problem. Actually, it turns out to be the key to the structure of the atoms of these elements, as to why, the problem is, why do we have this pattern of lights? So for example, is there any pattern? Is there any order to this series of lights of different wavelengths? Okay? It turns out it's not random. It is actually got a very important mathematical structure, which is related to the structure of the electrons in the atom. And so the first step, as when you have a tremendous variety of information, the first step is classify that variety of information in a logical order, like the periodic table. And so the first element, that's the easiest element, the element that is easiest to classify, turns out to be hydrogen, because it's the lightest element, it's got the simplest structure, and you can see that the light that you get when you analyze the spectrum of hydrogen is like a ladder, with red, blue, purple, 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 and these lines of light all come together very, very closely. But it's a nice mathematical structure where it suggests that there is a numerical pattern behind that structure. And the first person to, of course, many people recognize the pattern, but the first person to actually put a formula to the pattern was Balmer. Okay, I forget his first name. Anyway, what Balmer observed was that he could take these first 4 lines, 1, 2, 3, 4 lines of light, and find out their wavelength by using the instruments of the time that you could measure the wavelength, and that the wavelength of these lines of light actually formed an interesting pattern where if you had this number called 3645, then in succession you could get the different wavelengths by taking this number and multiplying by these integers, ratios, 9, 5, 4 thirds, 25, 21, 9/8. So now we are back to this whole situation like when we had the periodic table, right? 2, 8, 18, 32. Where's the pattern? Where's the pattern? So I thought of making a quiz question for you guys on this one. They said, no, that's too hard. Okay, to figure out the pattern of this. But if you read it, you know the answer, right? So this pattern is, in fact, a series. And there's 2 series in here. Okay? It looks at this as if it doesn't form a nice series. But what Balmer did was he multiplied both numerator and denominator of the second and the fourth term. This term and this term, he multiplied that. What did he do that? Where are we? Okay, so 950 kept, and this 4 he multiplied by 4, so that's 16, and this becomes 12. This he kept, and this one he multiplied by 4, so you got 36/32. So now you see what you got. The same number, right? 4 thirds or 16 twelfths. 9 eighths or 36/32. Same number. But now you see what you've got. You've got 9, 16, 25, 36. N squared. Right? 3, starting with 3. And then here you've got 5, 12, 21, 32. Can you tell what that is? N squared minus 4. Very good. So 9 minus 4, 16 minus 4, 25 minus 4, 36 minus 4. So the pattern is n squared divided by n squared minus 4. And that, okay, is exactly over here, repeated. And now he had a formula. The general formula is that the wavelength is this nasty constant times n squared over n squared minus 4. And he became famous. Okay, Balmer is known to be the first person who penetrated the spectrum of the simplest element, hydrogen. And then he put it in a more general sense of 1 over the wavelength is, he realized that this is 2 squared and this is n squared, where n can be 3, 4, 5. And here we have this number pattern in nature, once again, guiding us to the structure of nature. So what is the structure? Why do we have this pattern? So this was figured out by this Danish scientist, Niels Bohr, and this was all around the time of the, just before the Second World War, okay? 1940s or so, where Niels Bohr try to explain the Balmer series by imagining, remember how that leftover problem of Rutherford, here Rutherford's model of the atom was, you've got the mass and you've got the charge, the plus charge is blue and the minus charge is negative, and he had now simplified that to mean all this mass and all this plus charge is concentrated in the nucleus, and the minus charge is somewhere, okay, somewhere out there. So it's ants crawling around the football field, okay, or the baseball field. What Bohr figured out is how the ants crawl around the field. Okay. And the clue was the way they crawl around the field that gives out this light. And I'll show you how he constructed it. What he said was, I'm going to construct a place for these ants to crawl around in such a way that if they jump around from one place to the next, they'll give out light. Okay, and what makes them jump around is discharge or flame or something. You know, when you put a flame to an ant, it jumps around, right? So you excite the electron, and it'll jump around. And so he said, I'm going to arrange the places where the ants can move so that if this is the nucleus, the first place that they can move is in a circle around the nucleus where the circle has a radius of alpha. Okay, alpha. So I call that the Bohr radius. Okay, that's the radius of the smallest atom unexcited. Okay, that's the Bohr radius. Now the next circle where the ants can move is n equals 2 or n equals 3, and the next one is n equals 4. And so he constructed a series of orbits where the ants can move. And the reason he chose n squared, see, r equals alpha times n squared, is because that Balmer formula has n squared in it. Okay, so he used the Balmer formula to help him guide the path of the ants. So he fudged it, right? He used the experiment to guide his theory. So he said, in theory, these electron orbits have this formula, r equals alpha n squared, and these electrons can only be in these orbits. So if you now take the hydrogen atom, I can explain two things. I can explain why the spectra of light that comes out of the atom is discrete. In other words, why you get only fixed lines. And two, I can actually explain what the wavelength is, and I can explain the pattern. And here's the solution. So first he says, you got the nucleus, and you've got the first orbit, and let's suppose that there is an electron in this first orbit. Now, we put the other possible orbits out there. Okay, this is a hydrogen atom. It has a nucleus and one electron. Okay, it's finished. It's all settled. And now you excite it. Okay? How do you excite it? You put it in the discharge, or you give it a flame. And now when you excite it, the electron that was here jumps to a higher. Okay, there was the excitement. Okay, it jumps to the higher orbit. Okay, and then you remove your excitement, and so it jumps back. And when it jumps back, it emits light. Okay? And it can only emit light of the energy between these two orbits, or of the wavelength that corresponds to that energy. And so that's why you only have a single wavelength or a single energy of light coming out of this atom. Okay? So now he's explained what you call Balmer series, which means that you take any electron that jumps from any of these higher orbits to orbit number 2. Actually, it wasn't orbit number 1 that he used. He used orbit number 2 to explain what is called the Balmer series. So any of these higher orbits, if the electron jumps down, you get the Balmer series over here. Okay? Now, the important point about Bohr's model was he said, you know, you should also get another kind of series of light. Because if this is correct, then if there's an electron here, why does it jump to n equals 2? It could also jump to n equals 1, right? Which he ignored in the beginning. And he said, look for light that has this wavelength. Okay? And they went and looked for it, and they found it. So and the person who found it was Lyman, because that's why they call it the Lyman series. But here it says that from any higher orbit, if the electron jumps to the first orbit, then you get the Lyman series. Or you could have a different combination. You could have stuff jumping to orbit number 3, and then you get the Paschen series. Or you could get the Pfund series, and so on. And he predicted all of these series. And he also predicted what the formulas would be. So this would be the Balmer formula for the wavelength of light. Then he predicted that, come on. There we are. Sorry, I jumped too fast. He predicted that the Lyman series would have this formula, the Paschen series would have this formula, where you have 3 squared minus n squared, 4 squared minus n squared, 5 squared minus n squared, and the Balmer series is 2 squared minus n squared, okay? And the Lyman series is 1 minus n squared. So he predicted all of this, and all of this was found. Powerful theory, right? You come up with an idea, you predict new things, and you go find it. Then you say, he must be right. Bohr is absolutely right. But why do the electrons always crawling on these fixed orbits? Why can't they just move around any way they feel like? Okay, that he could not explain. Okay? So the explanation of that, why electrons can only move around in specific places, is the basis of this fancy word, quantum mechanics. Okay? So now you're going to be introduced to quantum mechanics. In fact, most people learn relativity first and the quantum mechanics second. You're going to learn quantum mechanics first and relativity second. This guy by the name of de Broglie, who said, you know, light is a wave. You all know that. We just saw that. He says electrons, you know, we're looking at electrons like ants crawling around the football field. He says that's wrong. He says electrons are not particles. Electrons are waves. Crazy fellow, right? I mean, all of a sudden he comes up with this idea, electrons are waves. But because of that idea, the reason he came up with that idea was that waves always form discrete patterns, okay? And he saw these discrete patterns in the atom, and he says that tells me that it's not planets going around the sun, but it's waves that are forming in orbits. So basically he was trying to make a string wave around the nucleus and calling the electron to be like a wave. So you've all seen waves, right? If you have, like I showed you that with Pythagoras' string, if you have a string taut between two places and you pluck it, it makes a wave, and you can pluck it in a different mode and you'll have a different wave. And so it's possible to pluck the string in many different modes, and you can actually have this guy plucking this electron wave moving in different patterns. And what's happening is not different orbits, but different patterns for the waves of the electrons. So now, is it on? Yeah. I need to turn some lights on here so you can see. All right. So what I've got here is a simple plate, okay? And I sprinkle some salt in it, and I'm going to attach this plate to a source of sound waves like this guy, okay? So the whole plate's going to vibrate, and you're going to see the vibration pattern of so first what I'm going to do is I'm going to kind of mix things up so you can see different patterns. Okay, now I'm going to turn on the sound, and I'm going to bring the sound to a particular frequency, like 187. And when I bring it to that frequency, you get a nice pattern in which the plate vibrates, just like the string vibrating, except now you're seeing a two-dimensional vibration. And the salt collects. The salt collects where the vibration is weakest. Okay? So the salt is collecting at the nodes of the vibration. So now you can hear that sound, right? Now I'm going to change that sound to a different frequency, a different sound. This is the same sound. Okay, now I'm going to go to a different frequency. Okay, I need okay, now you see that pattern? That's a totally different pattern because the wave is different, right? Now I'm going to do another one. And now I need some more salt. Because the salt does fly off the plate. And now I have a different pattern. So what de Broglie was saying was that there is energy in the atom, and now I got to shut this fellow off. There's energy in the atom, and because of that, and the electron is a wave, and because of the energy in the atom, the wave forms a certain pattern. And that pattern has a discrete geometric picture like this. And if you change the energy, just like I change the frequency of the vibration of the plate, you change the pattern. And every time you change the pattern, you get these different electron states, which Bohr calls n equals 1, n equals 2, n equals 3. And so the electron wave only exists in these patterns. Now, this is a fascinating idea, but it caused a lot of difficulties for people because they certainly knew that electrons are particles, because they saw the electrons in Thompson's tube behaving like particles. Okay? And now this guy is saying, forget it. Electrons are not particles, electrons are waves. But this experiment said electrons are particles because you made a shadow with the electrons. And now you've got waves. So what's going on? So now I'm going to give you some therapy that the answer is the electron is both. Particle and waves. Okay, so that's the heart of quantum mechanics. And the therapy for that is this work of art here. All right? By one of my favorite painters. And let me explain why that's therapy, okay? The therapy is, just read what he says about his own work of art. Okay? He says, I found a new potential inherent in things, the ability to gradually become something else. So for example, in certain areas, sky reveals wood. It seems to me something other than a combined object, since there is neither a rupture nor a limit between the two. And in this way, the painting forces the eye, or forces the mind, to think about things in a different way. So the electrons are both particles and waves. Okay? So sometimes we use the wave property to explain how it behaves, and sometimes we use the particle property, and we need therapy. That's it.